6. So let's choose another.
44.
44. Very good. So let's continue with 44. And 44 is f of x equals the cube root of 2x squared plus 1. Excellent. The problem was asking us, is it odd or even or none of the above? I have no clue. What do I have to start with? Always, for this question, what do I start with, no matter what? Anyone?
F of negative x.
Brilliant. F of negative x. So I have, thank you so much, Charles. So I have 2 negative x squared. There is no discussion there. So then I have 3 questions. Is this the opposite of f of x? Does this equal f of x, or none of the above? And I can only have yes to one and no to the other 2.
Even.
Yes. So I will say no, I will say yes, I will say no, and I will say even. Because it's identical, nothing changed. I plugged in negative x and nothing changed. It's still the same function. And that happens because the function is symmetric with respect to the y-axis. So the function is even. Awesome. So back to the plan. I think we had enough. We'll come back and do more problems when we review, I promise. Okay, I would like to continue with transformations. Okay, like with odd and even, transformations. Why? Who cares? Do I really need this? Can I have a nice life without transformations? Yes. Can I graph without thinking about transformations? Yes. Is it a bonus if I know transformations? Yes, it is. And I'll show you why. So transformations were addressed before. I will go through all of them, but just allow me to give you an example so you understand how important they are. Big deal? No. Like with symmetry? No. Not crucial. Not crucial. Interesting, nice to know if a function is symmetric or not. It's a bonus. It's a property of the function. But we can live without it. It's not major. Is this major? No. But it's very nice to know, and I'll show you why. So let's say we have the following function. I don't want to start with an example. I want to list something first. Sorry. So these transformations of functions are useful if I know, I don't want to jump into an example before I explain this. If I know basic functions. If I do not know the graphs of the basic functions, transformations mean nothing. I won't be able to apply them. I will not understand how to apply them. But if I do know the basic functions and their graphs, of course, by basic I mean pure. Pure. Very simple from each category, the simplest one from each category. So if I know their graphs of all basic functions, then this makes sense. If I don't know the graphs of all basic functions, nobody understands this, and nobody cares about it, and we cannot apply it. So in that case, let's list the basic functions first. Once we list the basic functions, I'll show you how useful transformations are. Again, I repeat, if we don't know the basic functions, these mean nothing to us. They will never help us. Okay, so let's list the basic functions first. So the simplest functions from all categories. Which page am I on? I'm on page 4. Okay. So, first category, linear. The simplest one is y equals x, of course. Not y equals x plus 1 or x over 2 or x minus 3. No. This is, under the category of linear functions, this is the easiest. The simplest, the basic one. And how will I graph it? Well, I need to know how to graph it because otherwise transformations make no sense. It's this graph. Odd, even, or none of the above. Odd, even, or none of the above.
Odd.
Excellent. Thank you. Of course, we are going to move on to what category?
Quadratic.
Of course. The basic quadratic function is this. Nothing on it. Plain, plain, plain. Okay, I know the graph. We just graphed it a minute ago, or 2 or 3. Here it is. Odd, even, or none of the above.
Even.
Absolutely. Thank you so much. Next one. Cubic. And the 4th degree. I want you to see them together. Not on the same graph, of course, but close. Okay, the cubic one is the one that we just graphed 5, 4, 6, 7 minutes ago. It's this one. It's a little flat here, because so you can say there are 3 solutions. Of course, there are not 3 solutions there, but multiplicity 3. So this is y equals x cubed. Odd, even, or none of the above?
Odd.
Of course, we just graphed it as an odd function. The 4th degree is identical with this, but flatter at the origin. It's because, presumably, we have 4 solutions there. Of course not, but we have a multiplicity 4. See the difference? This one turns quickly. This one turns but slowly. Closer, 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 closer. There is only one solution, but it takes longer to get closer to the origin. It takes longer to go away from the origin. So y equals x to the 4th degree. Odd, even, or none of the above?
Even.
Very good. Thank you so much. Of course, you see the resemblance. You see the resemblance. Degree 1 and degree 3. Degree 2 and degree 4. Okay. Continuing with the list. Number 5. Y equals 1 over x, which is rational. Very important function. And here's the graph. You're going to see this function in calculus a lot. So this is y equals 1 over x. Odd, even, or none of the above?
None.
It's an odd. Symmetry with respect to the origin. This piece is a mirror image of this piece with respect to the origin. Good. That was rational. Now let's look at radical. I'm on page 5. And which function was 6? Y equals the square root of x. So radical. Here's the graph. Odd, even, or none of the above?
None.
Very good. Not symmetric. Very good. Awesome. 7, absolute value. Here's the graph of the absolute value. Odd, even, or none of the above?
Even.
Thank you very much. Indeed. Okay, let's say 8, exponential. Odd, even, or none of the above?
None of the above.
Very good, of course. Not symmetric. Let's add one more. Log y equals natural log x. We graphed those last time. Yes, there are others like trig functions, etc., 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 etc. These are not the only functions. Odd, even, or none of the above?
None.
None. Very good. Not symmetric. So these are basic functions. If I want now, and now I'm ready for an example, that's my page 6. Let's say I want to graph 2x plus 1 minus 4. And I'm only interested in a shape or a quick graph. I will not use transformations to get an absolute 100% accurate graph. You could, we can. But the transformations are used just to give us a picture of the graph. I just made it up. I don't have a calculator. I'm not even looking at anything. So what I'm going to do, I'm just going to graph the absolute value of x in order of operations. Then I'm going to shift the graph 1 unit to the left, because that's what it means. This is the absolute value of x plus 1. Then it says multiply by 2 by stretching the graph by a factor of 2. So this will be my next step. I'm stretching the graph. This will go up here. So I'm stretching the graph. This is a rough graph, a quick graph. 2x plus 1. And then I know this whole graph has to come down 4 units. That's what the transformations are used for. A quick graph. Is this exact? No. 2 absolute value of x minus 1, x plus 1 minus 4. An exact graph will require the x and y intercepts, at least, which I did not determine. But I can. How do I determine the x and y intercepts? Can anyone tell us how do I find the x-intercept? And then later on, how do I find the y-intercept? For any function, any graph. Any function, any graph. How do I find the x-intercept?
You make y 0?
Exactly.
Or you set the equation equal to 0?
Exactly. So I have 2, the absolute value of x plus 1 minus 4 equals 0. How do I solve this equation? We had absolute value equations last week. What will be my first step here towards finding x?
Distribute 4.
I cannot distribute 4 because I have negative 4, so I have to move it to the other side.
Add 4.
Yes, add 4 to both sides. Now, please remember the absolute value is not parentheses. You are not allowed to distribute 2, ever, inside the absolute value. So then, in order to clean it up, what should I do?
Divide by 2.
Of course. And we had situations, we also had a homework. How do I proceed? I have to write that x. Go ahead, Ethan, go ahead.
Split it off into 2 equations, one where x plus 1 equals 2, and another one where x plus 1 equals negative 2.
Brilliant. So I subtract 1, so I get 1. I subtract 1, so I get negative 3. So I determine the x-intercepts. 1, 0. Okay, sort of. I'm close. And negative 3, 0. Okay, I'm close. By chance. I didn't calculate anything. Okay, now the y-intercept. How do we find the y-intercept? That was awesome. Thank you. I love when my students say something, even if you're wrong. It's okay to be wrong. So we can address this. How do I find the y-intercept for this function or any function?
You replace x with 0.
Excellent. 0 plus 1 is 1. The absolute value is 1. 1 times 2 is 2. 2 minus 4 is negative 2. Sort of. Not quite. 0, negative 2. So I was not too far. I will use again transformations when I need a quick graph. I need the shape. I graph the basic function first. How did I know? It's the absolute value. So I had to graph the absolute value of x. Then I shifted, in order of operations, I shifted 1 unit to the left. Then I stretched the graph, multiplying it by a factor of 2. I stretched the graph. And then I moved the entire graph 4 units down. So I had this in my head right away. That's the use of transformations. Not to graph 100%. Now it's almost 100%. I found the x and y intercepts. I know that this so-called corner is definitely at -1, -4. No question about it, that I know. And I have a rough graph quickly. That's what transformations are used for. Some of the books go through these steps and then they show 15 million points that they found, but what's the point then? If I find 15 million points to graph the function, then I'm not using transformations. So that's what transformations are useful. Once I know these graphs, I have these graphs in my head, create any function with these basic functions, and we will be able to graph it like we just did. Boom. If I want to find the x and y intercepts, then I have to do the algebra. Because here I could not determine them. I had to do the algebra to find those. So I just want to share my screen, and let's look at the next handout with transformations. And let's choose and let's work on any function that you would like to work on concerning transformations. Again, I don't consider this topic major, topic of any sort. Yes, it's good and it's nice to know. Here it is. This was dealt with in the previous class. So let's choose any function you want. So to illustrate again, you have all this information in here. It's on and on and on and on. It's kind of difficult to read, but we should go over some other problems. You choose. This was something similar with the one that I presented. This is also very similar. Let's choose other types of functions. Here's one based on x to the fourth. Here's another based on x to the fifth. We can also work on exponentials. And this was, we already discussed this property last time. We used this property last time. And we can graph this one if you'd like. You choose. So let me go slowly. So this was the end of the handout. So this is one function that has transformations. It's not a pure log. Pure log will just be log base 3 of x, done. No, it's log base 3 of x plus 1 with minus in front and plus 2 units. It has several transformations. A shift, a reflection, and a up and down, right? So that's 84. Let's see other examples. We can look at this one with exponentials. Or we can look at 4th degree, 5th degree. We can create one with a radical. We can create one with a rational. You can create any function you want, and we can illustrate transformations. Here we are given a graph to flip it. This is a reflection. So please choose. Don't say anything, I need to start a new video.